All right. In this video, we will be going over section 4.4. Section 4.4 is about indefinite integrals. Okay. Basically, in this section, we are going to define indefinite integrals, and we are going to see how to find indefinite integrals of certain functions. Okay. I want to start with this definition, the definition of an antiderivative of a function. Antiderivative of a function lowercase f is a function uppercase f whose derivative is lowercase f. Okay, let's see an example. For instance, suppose you have f of x. The lowercase f of x is equal to 2x. Can you find an antiderivative of lowercase f of x? According to this definition, an antiderivative of lowercase f of x is any function uppercase f whose derivative is lowercase f. Can you find a function uppercase f of x whose derivative is lowercase f of x? Okay, since we know the differentiation now, we can easily see that if you take uppercase f of x to be x squared, the derivative of this function is going to be exactly 2x. Okay, in that case, we say that uppercase f of x is an antiderivative of the original function lowercase f of x. Okay, remember, an antiderivative of a function lowercase f is a function uppercase f whose derivative is f. In that case, if you take f of x to be uppercase f of x to be x squared, the derivative of that function is going to be lowercase f of x. In that case, we say that uppercase f of x is an antiderivative of lowercase f of x. Okay, let me write it here. F is an antiderivative of lowercase f. Okay, now the question is, when I write this statement, I wrote n. Okay, what does that mean? That means there could be more than one antiderivatives. You can have infinitely many antiderivatives, and that family of antiderivatives is what we are looking for. Okay, so what is the family of antiderivatives? If you know that uppercase f of x is an antiderivative, what about this function? F of x, uppercase f of x is equal to x squared plus c. C is any constant. Would this be an antiderivative? Yes, because the derivative of x squared is 2x. That's good. The derivative of the constant is 0. So the derivative of this whole thing is 2x. That means this is also an antiderivative for any constant c. As you can see, here you have a family of functions because this c is an arbitrary constant. You can set this constant to be anything. Okay, so you get a family of antiderivatives. Once you have one antiderivative, in fact, you have a family of antiderivative. Okay, this is called a family of antiderivative because of this constant being arbitrary. Okay, let me write it here. This is a family of antiderivatives. Of the lowercase f. All right, next, let's go over this theorem, theorem 4.14. Functions with the same derivative differ by a constant. Okay, let's see the formal statement of the theorem. If f and g are differentiable functions, then f prime of x is equal to g prime of x if and only if g of x is equal to f of x plus a constant. Okay. All right, let's prove this theorem. Let me copy the theorem to the next page. All right, again, what this theorem tells you is that if f and g are differentiable functions, then f prime of x is equal to g prime of x if and only if g of x is equal to f of x plus a constant. Okay, that means if this statement is true, this has to be true. And if this statement is true, then this has to be true. That's what we mean by if and only if. If one statement is true, the other one should be true. If the other one is true, this should be true. Okay, let's prove this real quick. let's prove the forward direction first. That means if this one is true, let's prove that g of x is equal to f of x plus c. Okay. Forward direction. I will put this arrow to indicate the forward direction. Let f prime of x is equal to g prime of x, and we will show that g of x is equal to f of x plus c. What I'm going to do is I'm going to move my g prime of x to the left hand side. Minus g prime of x is equal to 0. Now, by the rules for derivatives, we can write this as f minus g prime of x is equal to 0. This is basically because the difference of derivatives is the same as the derivative of the difference. Okay. Now, as you can see, this is your function. F minus g is your function. The derivative of that function is equal to 0. What does that tell you? By theorem 3.6, that's the theorem that we discussed in chapter 3, we should have f minus g is a constant. Okay. Or in other words, you may write f of x minus g of x should be a constant. If the derivative of a function is equal to 0, that function has to be a constant. That means this function f minus g has to be a constant. That means f of x minus g of x has to be constant. Now, if you move your g of x to the other side, you get the desired result. G of x plus c. Okay, that's what you were looking for. Now, let's show the other direction. Now, assume that let f of x is equal to g of x plus c. We will show that f prime of x is equal to g prime of x. This is so straightforward. You just differentiate both sides of this equation with respect to x. If I differentiate the left hand side, you get f prime of x. If you differentiate the right hand side, you get g prime of x plus the derivative of c is a 0. C is a constant. That will give you f prime of x is equal to g prime of x. Okay. That completes the proof of the theorem. Okay. Let's move on. Next, I want to define indefinite integral formally. Okay. Let's see what we mean by an indefinite integral. Here is the definition. Definition 4.15. The indefinite integral of a continuous function lowercase f is defined to be the family of antiderivatives given by this equation. Okay, this is the family of antiderivatives where this f of x, uppercase f of x, is any antiderivative of your lowercase f of x. By the way, the indefinite integral is denoted by this symbol. You are familiar with this symbol by now, but as you can see, previously we had some lower bound and an upper bound, but in the indefinite integral case, you just have this integration symbol without limits, integration limits. Okay. All right. Here is how we denote the indefinite integral of a function f of x. Okay. And that is defined to be the family of antiderivatives. Uppercase f of x plus c. This uppercase f of x is any antiderivative of your lowercase f of x. Okay. That means it's a function. Uppercase f is a function such that f prime is equal to lowercase f. And here this f is called the integrand. Okay, this function, whatever the function you put here, is called the integrand, and this whole thing, this indefinite integral, is called the integral of a function of the function f of x. Okay, this is what we call the integral of the function f of x. All right, let's move on. We have from here onwards, we have some theorems. So let's go over one by one. Here is the first theorem we have, theorem 4.14, integrals of power functions. Okay. So here is the first part. If k is not equal to -1, then the indefinite integral of x to the power k, this is how you denote it. You put this integral symbol and then you put your function and then dx. Okay. The indefinite integral of x to the power k is going to be 1 over k plus 1 times x to the power k plus 1 plus c. Okay, how do we prove this? Proof. Part A. How do you prove that the indefinite integral of x to the power k is this particular function? As you can see, by adding a constant, you take a family of antiderivatives. Okay, all what you need to do is you need to show that this is an antiderivative of the original function, which is x to the power k. Would this be an antiderivative of the original function? Well, let's check that. I'm going to take f of x to be 1 over k plus 1 times x to the power k plus 1. Then clearly, if you differentiate this function, f prime of x, uppercase f prime of x is going to be exactly x to the power k. This is going to be x to the power k. That means x to the power k is your original function. Okay, that means this is an antiderivative of x to the power k. By the definition of indefinite integrals, the indefinite integral of your original function x to the power k dx is f of x plus c. C is any arbitrary constant. What is your f of x? Your f of x is this function. That's going to be 1 over k plus 1 x to the power k plus 1 plus c. Okay, so the indefinite integral of x to the power k is given by this family of antiderivatives. Okay, so the proof of these indefinite integral formulas are going to be very straightforward. And as you can see, the second part tells you that the indefinite integral of 1 over x is ln x plus c. Okay, how do you prove this again? All what you need to do is you need to show that this is an antiderivative of this function lowercase f. This is lowercase f, by the way. Okay, as you can see, this is your lowercase f. If you compare the definition of indefinite integrals, whatever the function you have here is your lowercase f. To show that the indefinite integral of 1 over x is equal to ln x plus c, all what you need to do is you need to show that the derivative of this function is 1 over x. Is that true? Yes, we know that it is true by our previous chapter. We discussed all the derivative formulas, and the derivative of ln of x is 1 over x. All right, let's move on. And then we have many formulas in several theorems. Theorem 4.17, integrals of exponential functions. Okay, if k is not equal to 0, indefinite integral of e to the power kx is 1 over k times e to the power kx plus a constant. Okay, again, to prove that this formula is true, all what you need to do is you need to show that this is an antiderivative of the original function e to the power x. It is clear, right? If you take the derivative of this function, it will give you this function. So the indefinite integral of this function is that antiderivative plus a constant. Okay, that's clearly true. And then if here is the second part of the theorem, if b is greater than 0 and b is not equal to 0, then the indefinite integral of b to the power x is given by this family of antiderivatives. Okay, this function plus this constant. Okay, again, if you want to prove that this formula is true, all what you need to do is show that this is an antiderivative of the original function b to the power x. That's clear here. Since you know the derivatives, if you differentiate this one, you get this back, b to the power x. That means this is an antiderivative of this function b to the power x. So the family of antiderivatives will be given by that particular antiderivative plus a constant. Okay. All right. Likewise, we have many other different indefinite integral formulas. I'm not going to prove each and every one of them. Let's state those indefinite integral formulas. Okay, here are the trigonometric indefinite integral formulas. Indefinite integral of sine x is equal to minus cosine x plus c. The indefinite integral of cosine x is equal to sine x plus c. C is any arbitrary constant. Okay, indefinite integral of secant squared x dx is equal to tan x plus c. And then the indefinite integral of cosecant squared x is minus cotangent x plus c. The indefinite integral of secant x tan x is equal to secant x plus c. The indefinite integral of cosecant x cotangent x is equal to minus cosecant x plus c. Okay, and I will briefly show you how to prove one formula. For example, how do you prove that the indefinite integral of cosecant x cotangent x is equal to this particular function? All what you need to do is show that this is an antiderivative of the original function. That means you differentiate this function and show that you get this function. Okay, if you differentiate this function minus cosecant x, what would you get? Minus times minus cosecant x cotangent x, that is cosecant x cotangent x, because two minus signs are cancelled. Okay, so that means this is an antiderivative of this function. Okay, now to write the indefinite integral of this function, all what you need to do is you add a constant to an antiderivative. You add a constant to the antiderivative that you found. This is an antiderivative. You add a constant to get the indefinite integral of this function. All right, we have more formulas. Theorem 4.19, integrals whose solutions are inverse trigonometric functions. Okay, the indefinite integral of 1 over square root of 1 minus x squared is equal to sine inverse x plus c. Okay, this formula is true because this is an antiderivative of this function. As you can see, if you take the derivative of this function, that is exactly this function. Okay, that means the indefinite integral of this function is that antiderivative plus a constant. Similarly, we have two more formulas. The indefinite integral of 1 over 1 plus x squared is equal to tan inverse x plus c. The indefinite integral of 1 over absolute value of x times square root of x squared minus 1 is equal to secant squared x plus a constant. Okay. All right, let's move on. We have another three formulas here. Integrals of hyperbolic functions. Okay, the indefinite integral of hyperbolic sine x is equal to cos x plus c, and the indefinite integral of cos x is equal to sin x plus c, and the indefinite integral of secant squared x is equal to tan x plus c. Okay. All right, let's move on. Next, I want to go over this theorem 4.21. Again, we have formulas for indefinite integrals. Integrals whose solutions are inverse trigonometric functions. Okay. Here, clearly, this is a typo. This is not inverse of trigonometric functions, but hyperbolic. Inverse hyperbolic functions. Okay. The indefinite integral of 1 over square root of x squared plus 1 is equal to sin inverse x plus c. And the second formula is indefinite integral of 1 over x square root of x squared minus 1 is equal to cos inverse x plus c, and the indefinite integral of 1 over 1 minus x squared is equal to tan inverse x plus c. Okay. All right, next theorem I want to go over is theorem 4.22, constant, multiple, and sum rules for indefinite integrals. Okay. This is very similar to the rules that we had in the definite integral section. Okay. If you have a function k times f of x, okay, k times the function f of x, then the indefinite integral of this function k times f of x is k times the indefinite integral of f of x. All what you do is you work this constant out. Okay. We did a similar formula when we were doing definite integrals. Okay, here also that formula is valid. If you have a constant multiplied by a function, you can pull that constant out. This is the constant multiple rule. Okay. And then the sum rule. If we have a summation of two functions, f of x plus g of x, the indefinite integral of that summation is the indefinite integrals, sum of the indefinite integrals of each function. Okay. The indefinite integral of the first function plus the indefinite integral of the second function. You can think of this as kind of you distribute this integral sign inside the parentheses. You take the indefinite integral of the first function plus the indefinite integral of the second function. It is similar to a distribution. All right, let's move on. And then we have theorem 4.23, reversing the product, quotient, and chain rules. Okay. So this is also some very important indefinite integral formulas. The indefinite integral of this particular function, f prime of x g of x plus f of x g prime of x. This should remind you something from the calculus 1. When we were discussing derivatives, what formula is this? Take the derivative of the first function, leave the second function fixed. Leave the first function fixed, take the derivative of the second function. This is the derivative of the product f of x times g of x, right? Okay. That means the indefinite integral of this function is f of x times g of x plus c. Why is this formula true? How do you show that this formula is true? All what you need to do is you need to show that this is an antiderivative of this function. You need to show that this is an antiderivative of this function. Can you show that? That's trivial. To show that this is an antiderivative, all what you need to do is take the derivative of this function and show that you get this function. Okay. As you can see, if you differentiate this function, you exactly get this expression by the derivative rules that we discussed in chapter 3. Okay. So the indefinite integral of this function is the antiderivative plus a constant. Okay, that's true. Similarly, you can see that this indefinite integral formula is going to be true. Okay, indefinite integral of f prime of x g of x minus f of x g prime of x divided by g of x squared is equal to f of x over g of x plus a constant. Okay, again, to prove this formula, all what you need to do is take the derivative of this function and show that you get this function. Or in other words, you show that this is an antiderivative of this function. That's so straightforward. Okay. And then the last formula we have is indefinite integral of f prime of g of x times g prime of x is equal to f of g of x plus c. Again, this follows from the fact that this is an antiderivative of this function. All right, let's move on. Next, I want to go over some examples. Here is the first example that I want to discuss. Which of the followings are antiderivative of f of x is equal to x to the power 4 and y? Okay. How do you determine whether these are antiderivatives or not? Let's work on the first part. Okay. How do I determine whether 4x cubed is an antiderivative of x to the power 4? All I have to do is, remember, antiderivative of this lowercase f is a function uppercase f whose derivative is lowercase f. Okay. So to determine whether this is an antiderivative, I'm going to differentiate this function and see whether I get this function. If I get that function, yes, this is an antiderivative. If not, it is not. Okay. So what is the derivative of this function? 4x cubed, the derivative of that function, I will denote the derivative by putting a prime like this, you get 12x squared. That is not what you want. It is not x to the power 4. So 4x cubed is not an antiderivative. 4x cubed is not an antiderivative. Of f. Okay. What about part B? Would this be an antiderivative of x to the power 4? Well, again, you differentiate the given function and see whether you get x to the power 4. If you take the derivative of this one, that's going to be 1 over 5 times 5x to the power 4. 5 will be cancelled. You get x to the power 4. As you can see, you get exactly this function. The derivative of this function is x to the power 4. That is the given function. So this is an antiderivative of the given function, lowercase f of x. Okay. In that case, we are successful. 1 over 5 times x to the power 5 is an antiderivative of your f. What about part C? Would this be an antiderivative of the given function? Clearly, yes, because if you take the derivative of that function, 1 over 5 times x to the power 5 minus 2, take the derivative of that. That is clearly, I'm not going to simplify, x to the power 4. Because the derivative of this function is x to the power 4, derivative of minus 2 is 0. So your derivative is x to the power 4, which is the given function. So that means that's an antiderivative. 1 over 5 x to the power 5 minus 2 is an antiderivative of f of x, or you may write of f. Part D. What about part D? Would this be an antiderivative of f of x? Let's check. Okay. If you take the derivative of that function, 1 over 5 times x to the power 5 minus 2, take the derivative of the whole thing. 1 over 5 walks out. Take the derivative of the inside function, x to the power 5 minus 2. You will get 5x to the power 4 minus 0, because the derivative of 2 is 0. This is what you get. This is exactly x to the power 4. So again, this is an antiderivative of the original function. So we may write 1 over 5 times x to the power 5 minus 2 is an antiderivative of f. All right, that completes the first example. Let's move on. Next, find the indefinite integral of 1 over x squared and the indefinite integral of square root of x to the power 3. Okay, let's work on the first part. I'll call this part A. Maybe this is part B. Part A. How do you find the indefinite integral of the first one? Indefinite integral of 1 over x squared dx. That is nothing but indefinite integral of x to the power minus 2 dx. 1 over x squared is x to the power minus 2. Okay. So how do you find the indefinite integral of x to the power minus 2? Well, we have a formula. Okay. What formula do we have to find this integral? Here is the formula, the power rule. Okay, the integrals of power functions. Okay, if you have x to the power k, the indefinite integral of x to the power k is 1 over k plus 1 times x to the power k plus 1 plus c. Let me copy this formula. All right, here is my formula again. So I can apply that formula here. As you can see here, the value of k is minus 2. Okay, so if I apply the formula, you get 1 over minus 2 plus 1, because you have 1 over k plus 1, k is minus 2, times x to the power minus 2 plus 1 plus c. Further simplifying this, you get minus times x to the power minus 1 plus c. Okay, that is the indefinite integral of 1 over x squared. And let's move on to the part B. In part B, we need the indefinite integral of x cube square root of x cube dx. I can rewrite this indefinite integral this way. The square root means 1/2 power x cube to the power 1/2 dx. Further simplifying this, you get the indefinite integral of x to the power 3 times 1/2 means x to the power 3/2 dx. Okay. Now I can again apply the power rule. Okay. This power of integrals of power function formula can be applied here. Okay. This is the value k in this case. So this would be equal to 1 over k 1 plus k or k plus 1 3/2 plus 1 times x to the power k plus 1 3/2 plus 1 plus a constant. Simplifying this, you get 2/5 times x to the power 5/2 plus a constant. Notice that 3/2 plus 1 is 5/2. Okay, you get the power 5/2, and this coefficient is 2/5. That's what you get when you simplify this. Okay, that is the indefinite integral of square root of x to the power 3. All right, that completes that example. Let's move on. Next, I want to go over this example. Find this indefinite integral and show explicitly how the sum and constant multiple rules for indefinite integrals are applied. Okay, let's see how to do this example. We need the indefinite integral of 5x to the power 3 minus sine x dx. Okay, you can view this as a summation. Okay, what you can do is this is nothing but 5x to the power 3 plus minus sine x. That means this is nothing but a summation of two functions, 5x cubed and minus sine x. If you add these two functions, you get this. Okay, so now actually let me write that here. This is equal to indefinite integral of 5x cubed plus minus sine x dx. Now I'm going to apply some indefinite integral formulas that we discussed today. Okay, what I'm going to do is I can distribute this indefinite integral symbol inside the parentheses. Okay, the sum rule. This indefinite integral is equal to indefinite integral of the first function. First function is 5x cubed plus the indefinite integral of the second function, which is minus sine x dx. Notice that my second function is minus sine x. Now I'm going to simplify this a little bit further. I can pull this out by the constant multiple rule. Okay, this is a constant times a function. You can pull this constant out. You get 5 times indefinite integral of x cubed plus, here I'm pulling this constant out. This is minus 1. If I pull this minus 1 out, this becomes minus. You get minus indefinite integral of sine x dx. Now all what I have to do is I need to find the indefinite integral of x cubed and I need to find the indefinite integral of sine x. Of course, we do have formulas for that. The indefinite integral of x cubed would be 5 times 1/3 plus 1 times x to the power 3 plus 1. And then I need to get the indefinite integral of sine x. What is the indefinite integral of sine x? Well, let's go and see the formula. I need indefinite integral of sine x. The indefinite integral of sine x is minus cosine x plus c. Okay, so this should be minus cosine x. Let me put minus cosine x. Remember, when I take the indefinite integral here, I did not put a plus c here, right? Here also I get a plus c, minus cosine x plus c. I don't have to put two different constants. Okay, I can put the constant, common constant for both of these functions. You don't. So if you simplify this, you get 5 over 4 times x to the power 4 minus plus, of course, cosine x plus c. Okay. All right, that completes that example. Let's move on. The next example I want to go over is this example. We need to find the indefinite integral of this particular function. Let's work on the first part. How do you find the indefinite integral of this given function? Well, here we are going to need some kind of imagination. Okay, there's no straightforward way of doing this. You need some kind of imagination to do a problem like this. Looks like this is a consequence of product of the derivative of the product of two functions, right? So to find the indefinite integral given here, you need to find an antiderivative of this function. That means you need to find a function whose derivative is this function. As I said, this looks like the derivative of a product of two functions, right? If you can figure out what product that would be, then we have an antiderivative. Can you find an antiderivative of this function? Well, if you try this function, uppercase f of x is equal to x times e to the power x. What is the derivative of this function or the derivative of this product? X times e to the power x. That's exactly this function, right? If you take the derivative of uppercase f of x, you get e to the power x plus x times e to the power x. That means this is an antiderivative of this given function. Once you have an antiderivative of the given function, then the indefinite integral is clear. Your indefinite integral is going to be the indefinite integral of e to the power x plus x times e to the power x dx will be the antiderivative plus a constant. Your antiderivative is f of x. That is x times e to the power x plus a constant. You are done. Okay. All right. Let's move on to the next part. As I said, we need some sort of imagination here. What about this one? How do you handle this one? How do you find the indefinite integral of this function? Well, for that, we need to find the function uppercase f of x whose derivative is this function. Can you think of a function whose derivative is this function? Clearly looks like we have applied the chain rule for a particular function, right? To get this function. Can you think of that original function, uppercase f of x, or the antiderivative of this function? What would be the uppercase f of x? That means a function whose derivative is this function. Well, it is clearly by observation. If you take uppercase f of x to be x squared plus 1 to the power 5, the derivative of this function would exactly be this quantity, this function given here. Because if you apply the chain rule here, you get derivative of f prime of derivative of uppercase f of x is 5 times x squared plus 1 to the power 4 times the derivative of the inside function, which is 2x. That's what you have here. Okay, that means this is an antiderivative of this function. Once you find an antiderivative, the indefinite integral is clear. What is the indefinite integral? The indefinite integral of 5 times x squared plus 1 to the power 4 times 2x dx is equal to your antiderivative plus a constant, x squared plus 1 to the power 5 plus a constant. Done. Okay. All right, now let's work on the last part. Okay, in the last part, we are asked to find the indefinite integral of this given function. Even though this function looks very complicated, if you carefully observe, you can see that this is a consequence of the differentiation of a quotient. Okay, so as you can see, by the way, first of all, to find the indefinite integral of this function, all what you need to do is you need to find a function uppercase f such that the derivative of the uppercase f is this function 2x tan x minus x squared secant squared x divided by tan squared x. Okay, so we need to find the function uppercase f whose derivative is this function. Okay, from the quotient rule, looks like this is your g of x squared, right? Then your g of x is tan x. So we are looking at a function like this. We have something in the top, in the bottom you have tan x, right? Now if you apply the quotient rule for this one, then tan x squared should be in the bottom, right? That's what we have here. So our bottom is okay. Our denominator looks should be tan x. According to the quotient rule for derivatives, your bottom function squared should be in the bottom when you take the derivative. Okay. Now you need to figure out what to put in the top. Okay. As you can see here, you have 2x. Here you have x squared. Looks like we have x squared in the top, right? Because you have x squared here and the derivative of that here. So I'm going to try x squared in the top and see whether if I take the derivative of this one, I will get this one. Okay. What do you think? If I differentiate this function, would you get this function back? Yes. By the quotient rule, we can clearly see that if we take the derivative of this function, you exactly get your uppercase f prime of x is equal to tan squared x 2x tan x minus x squared x secant squared x. Not tan x here, not hyperbolic. All right, so as you can see, this is an antiderivative of the given function because the derivative of this function is exactly the given function. Okay, so the indefinite integral of the given function is immediate. 2x tan x minus x squared secant squared x divided by tan squared x dx is equal to the antiderivative that you found plus a constant. Antiderivative that you found was x squared divided by tan x plus the constant. Okay, that completes that example. Let's move on. Next, again, we need to solve these indefinite integrals. That means we need to find these indefinite integrals. Okay, let's work on the first part. How do you find the indefinite integral of sine 3x? Well, first of all, we know that the indefinite integral of we need to find the indefinite integral of sine 3x dx. How do you find the indefinite integral of sine 3x? Well, again, all what you need to do is you need to find a function uppercase f of x whose derivative is this function. Can you find such a function? Well, if you take uppercase f of x is equal to minus cosine x, would that give you what we want? What is the derivative of minus cosine x? The derivative of minus cosine x is plus sine x, right? The derivative of cosine x is minus sine x. Minus times minus plus, so you get plus sine x. That's not what we want. We need sine 3x. What if we try this then? Instead of cosine x, what if I try cosine 3x? Would that give what I want? Minus cosine 3x. Well, if you differentiate minus cosine 3x, you will get three times sine 3x. Would you agree with me? If you differentiate this, you get minus sine 3x. That minus sign with this minus sign, that will become positive. You get, by the way, you have to apply the chain rule here. Okay, you have 3x So the derivative of this one would be minus sine 3x times 3. So the answer is 3 times sine 3x. That's not still what I want. I don't want a 3 here. See, I get a 3 here. How do I get rid of this 3? I put a 1/3 here. Okay. Now, if I try this function, as my f of uppercase f of x, if you take the derivative of this function, that derivative is going to be sine 3x. Okay. As I said, some sort of imagination is needed here. Okay. So now if you take the derivative of the uppercase f, you will get minus 1/3 times minus sine 3x times 3. This is 3, by the way. This 3 and this 3 will be cancelled. Minus times minus plus, you get sine 3x. That's what exactly you wanted, right? You wanted the function whose derivative is sine 3x. We just found a function whose derivative is sine 3x. So the indefinite integral is immediate. Indefinite integral of sine 3x dx is equal to the antiderivative you found, cosine minus cosine 3x divided by 3 plus a constant. Done. Okay. All right, let's move on to the next part. In the next part, we need the indefinite integral of x times e to the power x squared plus 1. How do you find the indefinite integral? Well, again, the idea is same. You need to find a function uppercase f of x so that the derivative of the uppercase of f of x is this function. Can you find a function whose derivative is this function? Well, so you have e to the power x squared plus 1. So let's try e to the power x squared plus 1. What is the derivative of e to the power x squared plus 1? The derivative of e to the power x squared plus 1 is e to the power x squared plus 1 times the derivative of this function, whatever you have here by chain rule, that is 2x. Is that what we want? Looks like it is almost looking like what we want. We want x times e to the power x squared plus 1, but we have 2x times e to the power x squared plus 1. Okay. How do you get rid of this 2? This 2 is unnecessary. Okay. This is not needed. We need this expression without 2. That way we get this one exactly. Okay. So how do you get rid of this 2? All what you need to do is put a 1/2 in front here and try that function. You put a 1/2 in front here. If you try to take the derivative of this new function now, this is going to be 1/2 times the derivative of this f of x. Okay. 1/2 times e to the power x squared plus 1 times the derivative of x squared plus 1, which is 2x. Now, as you can see, this 2 and 2 will be cancelled. Your answer is e to the power x squared plus 1 times x. That's what exactly you want. You want x times e to the power x squared plus 1. Of course, that is e to the power x squared plus 1 times x. They are the same. Okay. So now we found an antiderivative of this function. Once you find an antiderivative of this function, the indefinite integral is immediate. The indefinite integral of x times e to the power x squared plus 1 is going to be your antiderivative 1/2 times e to the power x squared plus 1 plus a constant. Okay. All right. This completes that example. Excuse me. We have one more part C. Let's work on the last part. Let me copy this to the other page. All right. How do you find the indefinite integral of 1 over 1 plus 4x squared. Well, again, the idea is same. You need to find a function uppercase f of x such that the derivative of uppercase f of x is equal to 1 over 1 plus 4x squared, right? That's the idea. How do you find such a function? First of all, you need to get some clue by looking at this function. What kind of a function should you differentiate to get a function like this? From the derivatives that we discussed in derivative formulas that we discussed in in calculus 1, we know that the derivative of, if I take uppercase f of x to be tan inverse x, the derivative of that function would be f prime of x would be 1 over 1 plus x squared, right? But this looks almost like this one, except for the fact that we have a 4 here. But this formula does not give a 4 here. That's the problem. Okay. Is there any way that we can get a 4 here? Remember, again, we need to find the function uppercase f whose derivative is this function. But we found the uppercase f of x, but the derivative of that function is not exactly this function. We get 1 over 1 plus x squared, but we need a 4 here. So can we try a modified version of this function to get this function exactly? Well, let's see. What about if I try my uppercase f of x to be tan inverse 4x? Instead of trying tan inverse x, I'm going to try tan inverse 4x. Then what is my derivative? F prime of x is equal to, pardon me, I'm going to try tan inverse 2x, okay? You will see why I'm putting 2 there. The derivative of this function would be, if I take my uppercase f of x to be tan inverse 2x, the derivative of that function would be 1 over 1 plus 2x squared, I'm applying the chain rule, okay, times the derivative of 2x, which is 2. Now, if you simplify this, as you can see, you get 2 over 1 plus 4x squared. That's what you get. Is that what you want, though? That's not what you want. To simplify this, you get 2 over 1 plus 4x squared. See? Here, this 2 is not needed. You need 1 over 1 plus 4x squared, but we have an additional 2 in the top. How do I modify now this original function to get rid of this 2? All what I need to do is put a 1/2 in front of this function and then take the derivative. That will give you 1 over 1 plus 4x squared. Okay. Now let me erase this one again. And let me put a 1/2 here. Now, if I take the derivative, that is going to be 1/2 times the derivative of tan inverse 2x is equal to 1 over 1 plus 2x squared times the derivative of 2x, which is 2. Now, this 2 and 2 will be cancelled. Your answer is going to be exactly 1 over 1 plus 4x squared. That's what you wanted. You found the function whose derivative is this function. That means this is an antiderivative of your given function. Now the indefinite integral is immediate. 1 over 1 plus 4x squared dx is equal to your antiderivative 1/2 tan inverse 2x plus the constant. Okay. All right. That completes our last example. I'll stop there and I'll see you next time.